Hello everyone, welcome back to NPTEL lecture series on cycloaddition reactions. Today's lecture is lecture number 5. So far we talked briefly about Diels-Alder reaction, particularly we discussed several examples on normal 4+2 cycloaddition reaction. So today what we will do, we will talk about the abnormal 4+2 cycloaddition reaction. That means inverse electron demand Diels-Alder reaction. In normal 4+2 cycloaddition reaction, as we know, the diene should have electron donating group and the dienophile should have electron withdrawing group. So today we talk about the abnormal, that is inverse electron demand Diels-Alder reaction, wherein you will see that the diene has electron withdrawing group and the dienophile has electron donating group. In the case of normal 4+2 cycloaddition reaction, the reaction takes place between HOMO of diene and LUMO of dienophile. But here it is exactly opposite. LUMO of diene and HOMO of dienophile are the ones involved in the orbital overlap. So take this specific example. So in this case you can see the diene, but it has two electron withdrawing group. One is ester, which is outside the ring, the other one is lactone, which is inside the ring. And the dienophile has an electron donating alkoxy group. So when you do this Diels-Alder reaction, then what you get is an aromatic compound. So you can have different substituent in the diene, you can have different substituent in the dienophile. Accordingly, what you will get is highly substituted aromatic ring. So what happens? The first step is the 4+2 cycloaddition reaction. You can see here. So this is the diene and this is the dienophile. Okay, these two undergo 4+2 cycloaddition to give this bicyclic intermediate, bicyclic 2-2 system. So now this undergoes a retro 4+2. This undergoes a retro 4+2, wherein you can see this carbon dioxide is expelled. Extrusion of carbon dioxide takes place through this retro 4+2. So how does it happen? If you write the structure now, so the carbon dioxide goes as the dienophile. Okay. Now what will happen? Once this diene is formed, then elimination of alcohol will give the corresponding aromatic ester. Okay. So this is one classical example of inverse electron demand Diels-Alder reaction. Take another example. So here, if you look at this example, it is cyclopentadienone. Cyclopentadienone, as you know, it is electron deficient. So you have a carbonyl group attached to this diene. Moreover, the cyclopentadienone are anti-aromatic, so highly unstable. But this can be stabilized by putting 4 aryl groups. These 4 aryl groups stabilizes this anti-aromatic compound. Now one can do inverse electron demand Diels-Alder reaction with various styrene. So if you do that, what you get is bicyclo 2,2,1 heptenone. Okay. Likewise, instead of styrene, if you use substituted acetylene, for example, if you use diphenyl acetylene, what you get is hexaphenyl benzene. So as in the case of first step, the Diels-Alder reaction takes place between tetraphenyl cyclopentanone and diphenyl acetylene to give this compound. This upon extrusion of carbon monoxide. Okay. So, this is called chelotropic elimination. So, extrusion of carbon dioxide gives the hexaphenyl benzene. Otherwise, this is not that easy to prepare. So, in one step one can easily prepare this compound. More importantly, this compound also one can easily prepare from corresponding diketone and ketone. So, this can undergo an aldol reaction to give starting material, that is tetraphenyl cyclopentadienone in one step. Well, there are many examples, we will discuss a few more. So, here again you have the diene with electron withdrawing ester group attached at carbon number 1, and you have a dienophile where the double bond is having electron donating pyrrolidine ring. So, these two will undergo Diels-Alder reaction to get this tetraline system, wherein the pyrrolidine group and the ester are cis to each other. You can draw the transition state, how we have discussed in the 4+2 cycloaddition. So, you can draw a similar transition state, and then you will see this is what you get. And look at this example. This example has one ester group at carbon number 1 and a carbonyl group at carbon number 3. Okay. So, this upon 4+2 cycloaddition reaction, obviously this is a inverse electron demand Diels-Alder reaction, can give another tetraline system. Okay. So, what is important is in this tetraline system you also have an alpha beta unsaturated ketone. But here if you see, this ethoxy group can undergo elimination if you heat it further. So, that will generate another diene. So, in the process if you see, what you got is you started with one diene having 2 electron withdrawing groups attached, and in the process you got another diene with 2 electron withdrawing groups, but the difference is it has one more ring. Okay. So, likewise you can keep on building rings using a combination of inverse electron demand Diels-Alder reaction followed by elimination. So, the next step, it undergoes further 4+2 to get this tricyclic compound. One can also vary, instead of this ethyl vinyl ether, you can use some other dienophile having an electron donating group. Okay. A similar example. So, now what you have is morpholine ring attached to a double bond. So, this is the dienophile and this is the diene, and this can undergo 4+2 cycloaddition reaction to give a tricyclic compound. Okay. Again, an elimination can take place to give this diene. If you leave it for some time, it can undergo dehydrogenation or air oxidation to generate the aromatic ring. Okay. So, you can see here from this compound, okay, it can undergo elimination to generate this diene, and once this diene is formed, either one can add another equivalent of dienophile to undergo one more 4+2 cycloaddition, or it can undergo dehydrogenation to give aromatic ring. Similarly, this compound can give a tetraline compound, okay, a tetraline with ester. Okay. So, this is also possible via a sequential 4+2 cycloaddition followed by dehydrogenation. And look at this example and compare with this. Okay. So, in this case you have a carbonyl group, here you have a lactone. Okay. So, you have one ester and a lactone attached to the diene. So, to make it a strong diene in the case of inverse electron demand Diels-Alder reaction. So, now you carry out this Diels-Alder reaction followed by dehydrogenation, you get a tetracyclic compound. Okay. So, this is another interesting method to generate an aromatic ring via Diels-Alder reaction followed by dehydrogenation reaction. This is a very interesting example where the dienophile is tetrasubstituted. The dienophile is tetrasubstituted with electron donating group, that is a tertiary amine which is attached to the vinyl group, whereas diene have electron withdrawing phenyl sulfoxide attached at carbon number 1. So, this can undergo this inverse electron demand Diels-Alder reaction to give this tetracyclic compound. So, this is a tetracyclic compound, and why it gives this endostereochemistry is because if you look at the HOMO of the dienophile and LUMO of the diene, still you can see the secondary orbital interaction. So, the secondary orbital interaction is the one which is responsible for getting this particular endo isomer. Okay. So, now from inverse electron demand Diels-Alder reaction, we will move to hetero Diels-Alder reaction. So far whatever Diels-Alder reaction we have discussed, if you carefully analyze whether it is diene or dienophile, you see only carbon atom. All the 4 atoms present in the diene are carbon atoms. Say likewise, both the atoms present in the dienophile are carbon atoms. So, why Diels-Alder reaction should undergo only with carbon atoms? Why not with heteroatoms? It is possible. So, there are many examples where heteroatom is part of the diene which can undergo Diels-Alder reaction. So, when you talk about hetero Diels-Alder reaction, there are 3 possibilities. One, the heteroatom is part of the diene. Okay. So, you can see here this is very well known dienophile actually. This is a very well known dienophile called acrolein, but it can also act as a diene. Okay. So, then this is also vinyl ketone, alkyl vinyl ketone. This also one can successfully use it as a dienophile in Diels-Alder reaction, but people also have used this as diene in hetero Diels-Alder reaction. Then you have imine, okay, the imine attached to a double bond. Okay. So, this is called azadiene. So, this also used successfully in hetero Diels-Alder reaction. In all these cases, if you see, you have a heteroatom. In the first 2 cases, you have oxygen atom. The next 2 cases, you have nitrogen atom as part of the diene. Then, like how diene can have a heteroatom, dienophile also can have a heteroatom. So, for example, if you take aldehyde, replace one of the carbon atoms of dienophile by oxygen, you get aldehyde, and now it can be attached to an aryl group or electron withdrawing group, or you can have imine. So, why only aldehyde? Imine also can undergo hetero Diels-Alder reaction. And why only carbonyl group? Why not thiocarbonyl? So, all these can undergo hetero Diels-Alder reaction and they will act as dienophile. Sometimes you will see hetero Diels-Alder reaction where the diene as well as dienophile have heteroatoms. Okay. So, then this reaction will have at the end a 6-membered ring with 2 oxygen atom or 2 heteroatoms. Okay. So let us start with heterodiene. Okay. So here it's a classical example. So if I have drawn it differently, but both are same. Okay, both are same. Why I have written this way? Because this acts as diene, whereas this acts as a dienophile. So now if you heat it, this can undergo a 4+2 Hetero Diels-Alder reaction to form this tetrahydropyran ring with aldehyde at anomeric carbon. And instead of acrolein, instead of dimerization, you take acrolein as the diene and simple alkene as a dienophile. In this case it is styrene, and you get a very interesting compound. Now this is a third example where instead of acrolein, what you have taken is methyl vinyl ketone. Methyl vinyl ketone and then this allylic alcohol. When you do this 4+2 cycloaddition reaction, you get a very interesting bicyclic compound. How do you get it? So what do you get first? You will get this intermediate. Okay. So now if you see, this is enol ether. Okay. If protonation takes place here, okay. Now this lone pair can neutralize the positive charge on the oxygen, that can give this product. So this is how you get, when you do this Diels-Alder reaction, in situ protected compound. Well, one can extend to cyclic compound. So here in this case this is acrolein, but you have one cyclopentene ring. Okay, the double bond is part of a cyclopentene ring. So this can undergo a 4+2 cycloaddition and can give this bicyclic compound. This anomer, you can see alpha and beta in 1:1 ratio, there is no selectivity. And if you take this type of diene, okay, then it's called arborine, and then you treat with acrolein, you get this product. Okay. And here why you get this? Because the diene approaches from the exophase. Okay. Normally whenever you have bicyclic system and having a double bond, always the electrophile or nucleophile or any reagent will try to attack from the exophase. And this is nothing but cinnamaldehyde. The cinnamaldehyde can undergo a hetero 4+2 cycloaddition reaction with this type of dienophile having 2 electron donating group, and that will lead to a very interesting monocyclic compound, and this is nothing but orthoester. Okay. So it can be hydrolyzed to a lactone, and this also during hydrolysis can undergo elimination of HCl to give this alpha pyrrole. So this is another interesting method to make alpha pyrrole in one step, and people have made such alpha pyrrole and utilize this alpha pyrrole as diene, heterodiene in several other Diels-Alder reaction. Okay. So why this particular regiochemistry is formed? Because the first bond is formed between this carbon atom and this carbon atom. Okay. That determines the regiochemical outcome of this Diels-Alder reaction. Then one can extend this with cyclic dienophile, and you also can have diene with 3 substituents, as you can see here. One is part of it, that is oxygen, then you have ester, but it is enol acetate. So this can undergo successfully 4+2 cycloaddition reaction to form this bicyclic compound. You can easily draw whatever I discussed earlier, how to write transition state for getting exclusively this product, and one can also extend this with another diene where instead of ester you have electron donating SPH group. This also can give this product, and this is the same example you can see here. So now instead of simple ethyl vinyl ether, you have extra methyl group, extra methyl group. So that means you will generate 3 new stereo centers in the product, yes, and all 3 are trans to each other. It's a relative configuration, but still the Diels-Alder reaction gives 3 new stereo centers. It can give maximum 4. So here you can see it gives 3 new stereo centers. So this is another classical example where the hydrogen bonding in the diene determines the regiochemical outcome. So here this OH is having hydrogen bonding with the carbonyl group. Now if you do the Diels-Alder reaction with the same enol ether, then this is the major isomer. So that is because of the hydrogen bonding. Otherwise, as you can see here, if you have acetate here, then you will get this as the major product. So this diene is in situ prepared. When you make this, it forms this enol, and this enol is having a hydrogen bonding with aldehyde. Now, if you take this amide, N-formyl acetamide, and then if you treat with TBS triflate, if you treat with TBS triflate, it forms this diene in situ. So N-formyl, so it can form enol, and then that enol undergoes protection with TBDMS. So this is how you get this. Once you have this diene, then it can undergo Diels-Alder reaction with dimethylacetylene dicarboxylate, and followed by hydrolysis you get this compound. So the Diels-Alder reaction should give you this 4+2 cycloaddition product in the first step. So now what happens, you can see, as we have discussed earlier with Daniszewski's diene, so this can undergo hydrolysis and so this will tautomerize to give this product. Now one can also use a cyclic diene having a heteroatom. Look at this. This has a cyclic diene with a heteroatom, and this, if it undergoes a Diels-Alder reaction, first step is the Diels-Alder reaction, and then second step is hydrolysis, and third step is LAH reduction. So what you get is vitamin B6. So how does it happen? Think about it. First step is 4+2. So what you should get is so this is the first step. This undergoes 4+2 to give this bicyclic compound. What's the next step? Is use of acid. So acid opens this bicyclic compound to give okay, and this one can write because this will undergo dehydration under acidic condition and this will undergo tautomerization, enolization to give this aromatic compound. So, now the third step is the reduction of ester. So, when you reduce ester, you get the corresponding diol. So, basically if you look at this, the vitamin B6 is prepared in 3 steps, starting from the diene, Diels-Alder, then acid catalyzed opening of the bicyclic ring, and along with that aromatization also happens, and then followed by LIH reduction gives the corresponding diol. So far what we have discussed is the heteroatom is present in the diene, but as I told you, heteroatom can also be present in the dienophile. So, this is Danishevsky diene, and now the dienophile as an aldehyde. Dienophile is an aldehyde. So, that means the carbon atom of the alkene is replaced by oxygen. One of the carbon atoms of alkene is replaced by oxygen. So, this can undergo Diels-Alder reaction as we have already discussed. So, this can undergo Diels-Alder reaction and followed by acid catalyzed hydrolysis will give you the corresponding pyrene ring. So, this is what you get first, then hydrolysis will give you the pyrene. Okay? And again, so this is the formation of this bond which actually decides the regiochemical outcome of this product. Then you can have electron withdrawing group, that is any diene with electron withdrawing group attached to aldehyde can undergo 4+2 cycloaddition reaction to give again this tetrahydropyrene ring. And instead of oxygen, one can also have nitrogen atom. Okay, if we have that, then this can undergo Diels-Alder reaction followed by hydrolysis to give this piperidone. It's a very interesting compound. Okay. So, now instead of starting with acyclic diene, if you start with cyclic diene, okay, then this can give this product where this ketone is formed from the corresponding enol ether. So, that enol ether undergoes hydrolysis during the acid workup. Okay. One can also use, as I showed in the first slide, you can use thiocarbonyl also as a dienophile. So, this can give you the 6-membered ring with corresponding sulfur being part of the 6-membered ring. Why should have only one heteroatom? Why not 2 heteroatoms? So, if you look at this compound, it has 2 nitrogen atoms. This can also act as a dienophile. So, upon 4+2 cycloaddition, this can give this very interesting heterocycle. Sometimes the dienophile cannot be, dienophile is unstable. Sometimes the dienophile is unstable and such dienophile can be easily generated in situ. For example, so the nitroso compound can be made from this Bach protected hydroxylamine. You take Bach protected hydroxylamine and then treat with sodium periodate. So, what happens is you generate Bach nitroso compound. So, now this is the dienophile and that can undergo 4+2 cycloaddition reaction. Okay. So, look at this interesting example. Okay, it is a ketone which undergoes this 4+2 cycloaddition with a diene, and the diene also at one side it is tetrasubstituted. Okay, tetrasubstituted diene is not that easy to undergo Diels-Alder reaction, but you can force it to undergo Diels-Alder reaction at high pressure. So now this way you could get this tricyclic compound, and that was used in the synthesis of a perfumery compound called amilanolide. So this is the key step. Then one can also use cyclic imines. Okay, one can also use cyclic imines, and this upon Diels-Alder reaction with Daniszewski's diene gives this very interesting tricyclic compound. So why this tricyclic is important? Because later this was converted into this natural product called phyllanthine, and the key reaction is this Diels-Alder reaction followed by hydrolysis. So there are many such hetero Diels-Alder reaction which are used as a key step in the synthesis of natural products. Sometimes, as I said, in the hetero Diels-Alder reaction, your diene as well as dienophile can have heteroatom. Okay. One such example is if you have a diol like this, then this upon treatment with periodinane reagent, it gives this very interesting tricyclic compound. Okay. So how does it happen? So basically what happens, this diol is cleaved to get this side alpha beta unsaturated aldehyde and that side also an aldehyde. So now if you look at this portion acts as diene and this acts as dienophile. So these two undergo an intramolecular 4+2 cycloaddition reaction, okay, to give this product. Okay. Since the stereochemistry is designed or determined by the stereocenters on the other ring, one can fix the stereochemistry of the newly formed chiral center. Okay. So there are many examples of hetero Diels-Alder reaction. So far we have been talking about intermolecular Diels-Alder reaction. So in the next lecture we will talk about intramolecular Diels-Alder reaction. There we also will talk about intramolecular hetero Diels-Alder reaction. Okay. So with this I will stop. Looking forward to next lecture. Thank you.